And our last speaker of the night is Scott Wilson, who is going to speak about equivariant extensions of holonomy and secondary invariants.
It's on. All right, so it's a pleasure to be here. It's an honor to speak here. Happy birthday, Dennis. He's always led by such a great example for all of us, that have been around him, and just has this great persistence and understanding and getting to the core of things, and yet at the same time has some amount of patience and generosity to go with it. So it's just a wonderful. It's been great to be exposed to so many great ideas. So I appreciate it a lot, and I think a lot of others, I can speak for them as well. So I wanted to, as Michael pointed out, that some of the audience maybe has changed a little bit in the last few days. The earlier talks a few days ago were more about maybe geometry and physics, and maybe there's a shift to dynamics. So I wanted to try to challenge myself and try to find something in the intersection. So I'm going to start with a picture, and the picture is going to suggest that these ideas of sort of derived algebra, really the physicists and geometers have been doing this at least since Cartan's time in 1950 or so, and maybe far before that, in studying dynamical systems. So that's the goal, is to start with this picture. So, and I should say two things. So this is joint work with Thomas Tradler and Mahmoud Zainalian, also in the circle, although maybe everyone's in the circle. And it stems from some hope to understand things about the free loop space of a manifold, but actually it relates more closely to Dennis's more recent work with Chern-Simons on differential cohomology. So let's start with this picture. So I need to have some kind of initial data. So for what I'm interested in this talk, I'm going to start with some bundle, E over M, with a connection, say nabla. And I want to study the holonomy of this, which, if you recall, is the parallel transport along a closed curve in the base of the manifold. So let me start with a closed curve, and it looks something like this. And I give it a base point, and I want to assume that maybe I can cover my bundle by local trivializations, and in each local trivialization I can study the connection and write it as a matrix-valued form. So I'm going to look at these local trivializations and cover the loop like this. And I have some open sets, U1, U2, U3, and they intersect on these overlaps. Now, if I want to study parallel translation along any of these charts, that amounts to solving some ordinary differential equation. And we know that from the theory that we can solve this ordinary differential equation using Picard iteration. And the solution, if I take my form AI in forms on UI, and these will be matrix-valued forms, so let me just write GL for matrices, then the solution of parallel translation along this piece is given by an integral. Let me write it in the following notation. For those physically minded, referred to by the physicists as the past-ordered exponential along the curve. And that gives me the answer, the solution to this ODE on each piece. And if I want to glue these pieces together, then I have to use the fact that the connection changes in each coordinate chart. And on the overlap, I have to take into account these transition functions. So I'm really looking at excuse me? Oh, this is a name
Do you need to show exponential?
No, it's important that I don't use it. This is, if these were abelian, if these matrices all commuted, then this would actually be e to the integral. But it's important in the non-abelian case that I don't take that. And I'm going to come back to that again. So let me write it this way. And you can imagine this is what I do on each piece, and then I sort of put them all together. So I want to explain how this picture actually suggests to us that we need some notion of derived algebra. So you might start studying this picture and say, well, I know that A is a form, and I understand forms on open sets, but somehow out of just that simple algebra of differential forms, I want to be led to such a formula. So you make the keen observation that forms on U1 intersect U2 is, say, a left forms on U2 module. And you also happen to notice that forms on U2 intersect U3 is a right forms on U2 module. And so you study that algebra, and you understand that perhaps you could take things like, say, the tensor product of forms when you have such left and right modules. And by chance, this is the wrong idea. So this is not the right sort of complex to be looking at to understand this formula. But what is the right complex is to take the derived tensor product here. And, well, that means something explicit in homological algebra. And actually, it's not a unique object. It's unique to quasi-isomorphism. But there's a particularly nice way to take the derived tensor product using some kind of explicit resolution known as the bar construction, which we heard about in the last two talks. And what that amounts to is taking sort of many tensors of forms on U2 and considering this complex. And this might look like nasty algebra at this point, but I'll show you in a second that it's exactly the complex one should consider in order to construct this. So,
can you just read that?
Yeah, this says
Rewrite it.
Okay. I'm going to rewrite the whole thing. It should be better the next time I write it, right? Yeah. And there are n of these. And I'm summing over all n bigger than 0. So, oh yeah, that's an intersection. So, for those in the know, this is a resolution using the bar complex. And the point is this. The bar construction constructs the domain of Picard iteration. So that's the point. And there's a natural element in this chain complex. And under a certain map, which I'll say in a moment, it maps exactly to the solution of this differential equation. So the map, I shouldn't write on that, but the arrow is going to go like this. The map goes to forms on, say, a neighborhood of this path in U2. And there's going to be an explicit element here, G12 tensor A, tensor A, tensor G23, sum, and it maps to this path exponential. And this map is known as the iterated integral map. It's essentially due to Chen. And I'm just going to sort of glue all these together and construct this entire holonomy around the loop. I didn't know that.
Yeah, but you used it to actually make the, you work with loop spaces
Right.
directly with the integrals.
Okay, so that's the punchline. So more generally, you can use the fact that you have forms on each open set, and on every intersection, those forms form a module on the left and on the right by the forms on the open sets. And you can perform this derived tensor product all the way around, not just on one collection like this. And so more generally, we have this complex. Let me just be really short. You're going to take many tensor powers. And there's a map called the iterated integral to forms on a neighborhood of gamma, this loop, in the loop space. And it sends a certain element here. Let me just denote it by h. It's just given by writing these symbols down next to each other to holonomy. OK, so that's the picture for a loop and when you have a connection on the bundle. And now you can sort of take this picture to its logical extent, where you replace a loop by a higher dimensional surface, and you continue. Since you asked the question about the exponential, I think maybe now is a good time to say that the following remark, which is that, well, I mentioned before, this holonomy is not equal to e to the integral of a in the non-commutative case. But it's very interesting that this complex actually turns out to be an algebra under a certain operation called a shuffle product. And the good news is that this map is not a map of algebras. And the reason why that's good news is that you can actually express holonomy as the iterated integral of a certain exponential of your data consisting of your transition functions and your connection. So what I mean by this symbol is there's a certain element, namely h. Well, there's a certain element whose exponential with respect to a product here is h. And under the iterated integral, we obtain holonomy. So the take-home message is, in the non-abelian case, one should exponentiate before integrating. And you do that algebraically, not analytically.
Actually incorporated somehow in the notation. Yes.
Yes. Yeah, and in fact, if you restrict to the case where these things happen to all commute, then, or for example, say you just take the constant a, then you'd be integrating a to the n over delta n, which has volume 1 over n factorial. And then you sum, and you do get the exponential. OK. So I'm making this remark because it'll be relevant later. So this sort of logical continuation, I think this is a really fun exercise, is you draw a surface, something like this, and you imagine breaking it up into pieces. And you cover every piece by a chart. And you ask yourself, what is the algebraic structure of, say, differential forms that's present here? And it's very interesting. You have forms that are in algebra, and on the intersection, that's a module on the left and on the right. And those themselves form an algebra, and they have an intersection in the middle is a module over forms on the double intersection. And it's, well, it's kind of a rich structure of algebras and modules, which are also algebras, and modules over them, and they're compatible. And one can write down a complex in a very similar way using that with the notion of a derived tensor product. OK, so these pictures are more relevant when one studies generalization of a bundle called a gerbe. And A gerbe is, well, these are related to what we heard about earlier in the week, differential cohomology. They're sort of the next, they're geometric representatives for differential cohomology 1 degree higher than those that represent line bundles with connection. Okay, so what can one do with this picture? So I wanted to just give kind of some results on how one can use this algebra and this notion of integrals, which construct forms on, say, the loop space or the space of maps of a torus into a manifold. So here's a theorem that's due originally to Bismuth. And there's a very nice proof of it using the techniques that I just presented. So let E with a connection be a bundle. And the statement is there is a equivariantly, S1 equivariantly closed extension of holonomy So the statement is that there's an S1 equivariantly closed extension of holonomy to a total even form on the loop space whose restriction to the constant loops is the usual Chern form associated to the connection on the bundle. And the way one way you can prove this using the techniques I just mentioned is to study the holonomy and its derivative, and study the circle action on the loop space.
Holonomy and omega 0 mean?
Yeah. So this is, well, it's the function on the loop space that assigns the holonomy around a loop. Yeah. So I'm slightly, I'm at some point I switched when I had matrix valued forms and I stopped writing matrices, and now I'm not really writing where the values are, but they live in a certain endomorphism bundle.
All right.
And one can take trace and then obtain the ordinary Chern form, which is defined using trace. So, okay. Let me state a theorem now that goes with this picture. So the statement is that let G, A, B be an abelian gerbe. So in a moment, I'll say why you can think about that as being like a line bundle with connection on the free loop space over a manifold. And then the statement is that there is an S1 cross S1 equivariantly closed extension of what's called the 2 holonomy in the forms on maps of a torus into M whose restriction to a certain subspace of the space of maps of torus, I'll explain that in a minute, equals the Chern form of the line bundle on LM associated with connection associated to this gerbe. So this sort of requires some explaining. So as I mentioned before, abelian gerbes with connection have a notion of sort of parallel to transport. And in the case of a closed surface, we call that the two holonomy. And the statement is that this two holonomy, this zero form, extends to a, actually, just as before, an even form on the torus mapping space. And you can restrict that form to a certain subspace. Now, what is this subspace? These are what we call thin tori. So if you have a map of a torus in, you could consider those maps of a torus which crush one factor. And those are what I'm calling thin tori. You can identify that with a loop space. There's actually more than one way to do that, but let me just, I have a particular one in mind. And then this nice compatibility result that one can take a gerbe, an abelian gerbe with connection, and associate to it a line bundle on the loop space. And then this restriction just recovers the ordinary Chern form of that line bundle with connection. Yeah?
What do you mean by parallel to transport?
Probably not quickly, but roughly what I mean is it's something like, well, parallel transport in the situation of around the loop was like the integral of, it was roughly like e to the integral of a, say in the abelian case. In the case of a gerbe, this b is a 2 form, and this is actually a 1 form. And this 2 form, the 2 holonomy is roughly like e to the integral of b over this surface. Though that's not literally true because you don't have a global 2 form. These are only true locally. So the idea of a gerbe is you sort of, the way the physicists discovered it is you say, suppose I had a 2 form on my manifold, but I didn't have one globally, I only had it locally. And then you ask yourselves, well, they call it the B field, but they want to be able to integrate over this little patch, and they'd like to be able to do some exponential version of it and have it be well defined. So you could discover the definition of a gerbe just by sort of asking for that condition and saying, well, I need some kind of 1 form on the overlaps that correct things. And then you'd say, well, but on the double overlaps, that wouldn't really be well defined, so I need some kind of function on the triple overlaps, and you'd keep going. And this leads to the notion of a gerbe. And 2 holonomy is, some invariant associated to it, just like holonomies and invariant bundles. Okay, so I promise no one will miss the bus, which gives me 1 minute. So, all right. No, I actually just wanted to draw a picture for the last theorem. So the picture for the last theorem goes like this. So recall that if you have a path of connections, you can construct something called the Chern-Simons. So I'll call it Chern-Simons term that interpolates between the Chern form at the endpoints. So you take your path of connections. You have a connection at each endpoint. Each one of them has a Chern form. And the Chern-Simons term is an odd form whose d is the difference between these Chern forms. And it gives rise to a secondary invariant. For example, when the Chern forms are equal, or when they say both vanish, then this odd form turns out to be a closed form. And in that sense, it's a secondary invariant. And the theorem that I want to state is that given a bundle with connection, with a path of connections, AT, there is, and let me just draw the picture. I'll draw a picture on LM. These are forms on LM. And I'll draw a picture. Well, I have a picture here. I'm going to write here I'm going to write B of A0 for the Bismuth form that is in this previous statement. And another B of A1 for the bismuth form. And the theorem is that there exists a form, let me write it as this. There exists an odd form associated to a path of connections whose equivariant differential is the difference. In other words, this shows several things, but there's an odd form whose equivariant D is the difference between these two. That shows that this bismuth form is well defined as an equivariant cohomology class. But an additional property is that this entire structure on the loop space, these forms, restricts on the manifold to give the Chern-Simons form that interpolates between the Chern characters. So this is a sort of equivariant extension to the loop space of the Chern-Simons form. And there's, in the interest of time, I'll stop, but there's a completely analogous theorem to this, where you replace line bundles with connections and the loop spaces by gerbes in the torus mapping space. So maybe I'll leave it there.
Any question? The boss is not there yet, so you can have long questions.
I just heard it come.
Can you just repeat that?
Can you really write down, as it were, explicitly a thing like the bar construction that applies to the two-dimensional illustration?
Yeah, and it's not due to me. It's something called the higher Hochschild complex. So I mean, what I was dealing with before in the case of the loop space was secretly the Hochschild complex, where you think of the circle. And there's a theory that goes back to Pirashvili of higher Hochschild complexes sort of for any simplicial set. And well, these higher Hochschild complexes for commutative algebras have been shown recently to be related to factorization algebras due to Stradler, Zanellian, and Junot. But you can literally write down such a complex. And it's d squared is 0 by all the algebra that's suggested in the picture of the modules being compatible.
You're considering here the pre-loop space and the space of maps from the torus S1 cross S1 into N. Is there any you can see for generalizing this model?
Yeah. So
mapping spaces.
yeah. So
What was the question?
he said, "Do you want to say it?"
No, yeah.
He said, "Is there any hope that you could generalize this to more general mapping spaces or higher dimensional things?" So the algebra is already in place. These higher Hochschild complexes exist, and I imagine you can plug in higher gerbes to them. There's all the algebraic structure is sitting there, sort of waiting to be used. The calculations are a little messy, when you want to write down a complex with three-dimensional, but they're there, and it's hard to imagine that it couldn't be done. Oh, I don't know.
So is there an analog of this time-ordered exponential formula for surfaces? Can you actually write it down?
Yeah, you can write.
Could you repeat the question?
Yes, is there an analog of this path-ordered exponential for surfaces? And the answer is yes. You can write it down explicitly, and you don't even have to work very hard, because the reason why is that you take this viewpoint earlier, you take this remark, which is that the iterated integral is there once and for all. You can just express that as like integration along the fiber, like a la Chen's theory. The exponential map in the torus case is also there, because these complexes all naturally have some shuffle product, and that's their product. And in any commutative algebra, e.g. shuffle product, you have an exponential map. And so it just falls out naturally.